Ушла.
Okay, shall we start? Today we have internal speaker, our new PhD student, not our, new PhD student, Timur Pryadilin, who graduated from Cambridge University, and he present us something what we did there. Yeah.
Not in Cambridge, actually, in last summer in Vienna.
Okay.
Yeah. Yes, thank you. So yes, this talk, I'll talk about transition to turbulence in pipes. So it will mostly be, so since I expect that most people here are not that interested in fluid dynamics, so it will mostly be a review of the history of this question, because it's very interesting. And yes, so I joined this group that was doing this research last year, and I don't think I'll have time to talk about the research I was doing, but I hope will be an interesting talk. So I'll start with a bit of history, and I'll start with this famous equation, which I think everybody here has seen. So this is what we call Poiseuille's law, and it describes how a pressure gradient in a pipe will drive a flow of fluid through this pipe, and was actually not first published by Poiseuille. It was first published by Hagen. There was some controversy. Then there was an explanation of this law by Stokes, and was one of the first explanations of his theory of viscosity. But quite quickly in the 19th century, people realized that this law is not universal for pipes. It only applies to slow flows in some sense. And for higher rates of flow, there were some other alternative theories of the law of resistance. And the first systematic study of the transition from the validity of this law to some other regimes was done in 1883 by Reynolds. And this was the study where he introduced the quantity which we now call the Reynolds number. And it's a dimensionless quantity, which for pipe flow is usually defined as the mean flow velocity times the diameter of the pipe over the kinematic viscosity of the fluid. And on dimensional grounds, he argued that this number is what defines the character of the flow inside of the pipe. And he said that since we know that there is a transition from one type of behavior to another, then there should be some sort of critical value of this parameter, such that below this critical value there is one regime where this law applies, and above this critical value there is a different regime, which we would now call turbulent. And so he depicted his findings, and he said that at slow velocities, if he adds dye to the entrance of a pipe, then the dye flows in a straight line, and he called this direct flow, and now we call it laminar flow usually. And if the velocity was higher, then the same dye would still propagate in a straight line until some point where it would break into multiple eddies and mix around. And he called this sinuous motion, and now we call it turbulent motion. And he tried in his experiments to pinpoint the exact value of the Reynolds number where this transition occurs. And he immediately faced a lot of obstacles with this quest. And so I'll quote from his work that he said that the critical velocity turned out to be very sensitive to disturbance in the water before entering the tube. And the steady motion was unstable for large disturbances long before the critical velocity was reached. So he said that it's very hard to measure the system because it's very, very sensitive to how you organize the experiment. And in his experiments, he could observe this transition for Reynolds numbers going from 2,000 to 13,000. So it was a very wide range. And he left the physics world with this quest to pinpoint more precisely where this transition from laminar to turbulent flow actually occurs. And so this was formulated in 1883. And the final answer to the point where the transition occurs and how the transition works was only given basically last year in 2024. So I think it's one of the oldest open problems in physics, which was recently resolved. But this attracted the attention of physicists immediately. And the first idea to study this problem was the idea of linear stability or instability. And so people try to imagine an infinitesimal perturbation to the laminar profile and calculate whether it will, whether it will grow or decay. And this linear analysis actually has a very rich history of people who worked on it, because it included Kelvin, Rayleigh, Lorentz, and even Werner Heisenberg actually had his PhD thesis on linear instability in pipes. And the experiments were also actively investigating this problem. And the experiments show that this question of linear stability doesn't seem to be the right question, because if the experiment is clean enough and without any disturbances, then Reynolds numbers up to 100,000 can be reached, as was done in the 1960s. And mathematically, there was finally a proof achieved that for all Reynolds numbers, no matter how large, the flow is actually linearly stable. So it was first shown for a range of Reynolds numbers up to 10 million. And then 6 years ago, there was finally proved that for all Reynolds numbers, the flow is linearly stable. So this put an end to the study of linear instability scenario to turbulence. And in particular, since there is no linear instability, we cannot have a bifurcation scenario, which is common in other types of turbulence, where at some finite Reynolds number, there is a bifurcation of the flow. And then at high Reynolds number, there's another bifurcation, and then there's a cascade of bifurcations, and then a chaotic region at some critical Reynolds number. So this scenario cannot happen if we don't have the linear instability to start with. So people had to find alternative ways to define the transition from laminar to turbulent flow. And since linear instability doesn't work, people started looking at what happens if we apply finite perturbations. And it became clear that if we do that, then very consistently, we seem to get very similar structures appearing. And people call those structures turbulent puffs. And actually, even Reynolds himself observed those puffs. So here is a sketch from his work. And turbulent puffs are regions of turbulence in a pipe, which have a very specific length, and they do not expand when they do not usually contract. And in between these puffs, there are regions of laminar flow. So there is an intermittent turbulence here. And these puffs, they are propagating downstream with the flow approximately at the mean flow velocity. And experiments show that these puffs are usually observed for Reynolds numbers from 1600 to 2400. So a fairly narrow range. And here's a brief illustration of what these puffs are in terms of their internal structure. So this comes from 2 different research papers. On both figures, the water flows from left to right. And puffs have a fairly sharp edge in the upstream direction, and they have a sort of wiggly long tail of turbulence in the downstream direction, which can actually change in length slightly. It oscillates here randomly. And their internal structure is turbulent, but it's not a developed turbulence. So for example, Kolmogorov's law doesn't apply here because the Reynolds number are still not too large. So this is roughly at the point of the turbulent transition. But there was a lot of research on their internal structure, and we know quite a lot about them. And one of the key properties of puffs is that they're not stable structures, in a sense that if you have a puff, it will propagate for a while, but then inevitably it will decay into a laminar flow. And oh yes, I was going to say that the reason puffs are interesting is that for the range of Reynolds numbers where they occur, they are in some sense a universal outcome of whatever perturbation you apply. And here's a very nice figure from a recent research paper, which shows 4 different ways you can inject water into a pipe. And if you inject it smoothly enough, then you just get a laminar profile all throughout the pipe at sufficient distance downstream. And if you have some sort of perturbation at the entrance, some sort of obstacle, then you'll mostly get a laminar profile, but you'll also get those spontaneous peaks in pressure in this case, or whatever you measure. And those will correspond to puffs, which appear at a sufficient distance downstream. So no matter what you have at the entrance, after a few hundred time units, your flow is gonna decompose into laminar flow and puffs at certain locations. And an interesting thing is that if you perturb your flow in a specific way, basically slam it with a hammer, so the delta function impulse at equal intervals, then you can create puffs which are equidistant at sufficient distance downstream. So this shows that on the one hand, no matter what kind of perturbation you do, you always get these puffs. And also there is a way to reliably get them at the locations where you want them with a specific technique in experiments, which is quite useful for studying them in an experiment. And as I said, the puffs, they're not stable, they're metastable in a sense. So they have some mean lifetime that, which depends on the Reynolds number. And with increasing Reynolds number, people observe that they become more and more stable. So they survive for longer and longer times. And we can quantify this by measuring the probability for them to survive after a certain amount of time. And it turns out that puffs, the decay of puffs is a Poisson process. So there is always a constant rate of probability to decay from a puff to a laminar flow, which doesn't depend on how long the puff has existed already. So they're statistically equivalent to each other at each point in their evolution. And so here is an experimental paper which shows that it measures the probability to survive after a certain amount of time for different Reynolds numbers. And for all Reynolds numbers, it's pretty much a straight line. And another thing which you may notice is that as the Reynolds number increases, the probability to survive becomes higher and higher and higher. So the lifetime of puffs becomes larger and larger and larger. And one of the ideas at the time, in the early 2000s, was that maybe the critical Reynolds number at which the transition from laminar to turbulent flow occurs is the one at which the lifetime of these puffs becomes infinite. So it diverges, maybe it diverges a certain Reynolds number. And this was a promising idea, and there was a lot of experimental data which seemed to support it. And the implication would be that if the Reynolds number is smaller than that, then all the puffs will initially be triggered, but then they will decay into nothing. But then above this critical Reynolds number, the puffs will continue to exist forever. And so this will mark the transition from laminar to turbulent flow. Unfortunately, this was not the case. And careful experiments show that, in fact, the lifetime of puffs grows very, very quickly, at least exponentially, with the Reynolds number, but it doesn't converge to infinity. So here's the inverse lifetime of puffs versus the Reynolds number. And the vertical scale is logarithmic. And there is almost a straight line here. So we don't see a divergence to negative infinity, we just see a straight line. So the lifetime does grow very quickly, but it doesn't become infinite. So this was not the right answer to the transition of turbulence. However, the next piece of the answer about the transition to turbulence came from the observation that the puffs are not just capable of decaying into nothing, they can also reproduce themselves. And this is a phenomenon called puff splitting. And so here is some visual demonstration. This one's from experiment, and this one's from direct numerical simulations. And here you can see that if you start with a single puff with a sharp edge and a long tail here, then after a certain time, there is a chance that it will split into two peaks in the pressure distribution. And if you wait for a longer time, they will push each other out, and there will be two puffs formed at some distance from each other. And here is a space-time plot, so time goes in that direction, and this one in this direction represents the length in the pipe. And we start with a single puff in the space-time diagram with a sharp edge on the left and a long turbulent tail on the right. And we see that at some time, the tail becomes so long that it triggers a perturbation downstream from it that is sufficient to create a new puff appearing at distance downstream, and then they separate slightly. So we start with one puff, and then this puff has created a new one. So there is a reproduction event that is possible. And the measurements have shown that if you measure the probability of not splitting after a certain amount of time, then it's also an exponential distribution. So it's also a Poisson process, a memoryless process. So at each point, a path has a certain rate of decay and a certain rate of splitting. And an interesting question was, how do these two effects compare? And what happens if we plot the mean time of decay versus the mean time of splitting? And intuitively, we expect that for increasing Reynolds number, the paths become more and more stable, so that their lifetime should increase. And they also become more and more able to reproduce, so their time for splitting should decrease. And there was...
I have.
Yes.
What determines the position of these paths?
Well, initially they're determined by the perturbation you apply to the entrance of the pipe. So, for example, if you smash the pipe at equal intervals, then you're going to get.
So they move
Yes, they move with the flow, roughly with the same velocity as the flow.
with the same velocity.
Well, yes. So there is mean flow velocity, and the speed of the path is like 95% of that usually,
Okay.
something like that. So you have a lot of control over their location, but they also have a random component to their velocity because they're still turbulent in their nature. So the velocity is not exactly constant, but there is some distribution of velocity around some mean value. And I'll talk about that later because it turned out to be quite important. Yes, so here is what happens if you plot the mean time of decay and mean time of splitting. And this was a remarkable figure because it was a result of years of research of these paths by different groups. And we see that, well, indeed, as we expected, the two curve, this curve is growing, this one curve is decaying with the Reynolds number. And there is some critical Reynolds number where the paths are just as likely to split and to decay. So we expect there to be some sort of balance here. And here they're overwhelmingly more likely to decay, and here they're overwhelmingly more likely to split. So there is some sort of transition going on near this intersection here, where the paths go from decaying into laminar state all throughout the pipe to splitting so much that they can sustain some fraction, some equilibrium fraction of them in a pipe. But what is remarkable about this plot is the axis of this plot. So the horizontal axis is linear here from 1800 to 2400 in Reynolds number, so quite a narrow range. And the vertical scale is logarithmic, and it goes from 100 time units to 100 million time units. And the intersection occurs at roughly 10 million time units. So this is a very, very long time scale for a single reproduction or decay event near this critical point. And this gives a partial answer to the question why this research took so long to do, why Reynolds didn't figure out this himself. Because if you want to measure these things, you need to be conducting experiments for incredibly long times, up to 10 million time units, even for a single event to be observed.
By the way, this is for water or for which?
Well, in principle, this should be.
It doesn't.
Well, the experiments are usually done with water, of course, because it's the most accessible liquid. But in principle, well, any liquid has a certain kinematic viscosity. So, and it will have, if it's, well, unless it's a non-Newtonian fluid, this should apply for all fluids.
So the result is shown for the simulation, right? The result is the result of simulation, but not experiment.
No, some of these are experiments, some of these are simulations. So DNS are simulations. So these black points are simulations. And these colorful points are all experiments. And these black points are also all experiments. So this was still possible to measure in an experiment. So let me summarize what we have so far before we go to the next step in the logical algorithm.
How do they measure lifetime of path?
So yeah, that's a good question. So usually you trigger a path and you measure whether it survives up to a certain distance downstream. So you put a pressure detector some distance downstream, and you measure whether there is a path getting to that pressure detector or not. And some fraction of them will get there and some fraction will not. So you can measure a survival function as a function of distance downstream. And then you get the plot of survival function, and you fit it with a straight line, and this gives you a survival time.
But is the inverse process to the path decay? Can a path be created downstream?
So from
from some fluctuation?
Yes. Well, if you just have a laminar flow, then it will not spontaneously. So a laminar flow is stable. If you have a precise laminar flow, it will not just appear from nothing. But if you have a puff, it can create due to its own.
Now, suppose this puff is decayed.
Okay.
We look still further downstream. Can it be measured again?
If the experiment is conducted well enough, it will not appear again. So if it decays forever. Yes, and that's actually important. So let me quickly summarize again. So we have those units of turbulence which propagate in one direction. So they fill out the whole cross-section of the pipe, and they only move in one direction. They can undergo stochastic decay and reproduction. They cannot appear from nothing. And we expect some sort of transition to occur where they can sustain some equilibrium density. And the question which was asked in the research community was if there are systems that have been studied that have similar properties. And the answer is yes, there is a system which has a lot of similar properties. And the system...
I wanted to ask from the beginning. So when you say about modeling, you are talking about Euler equation.
Navier-Stokes equation.
Navier-Stokes.
So
with some boundary condition on the pipe boundary.
Well, at the boundary of the pipe, we assume no slip boundary condition usually, so zero velocity. And there are facts about the edges of the pipe, how you model it. So sometimes you apply a periodic boundary condition in direct numerical simulations. Sometimes you just get a very, very long pipe and simulate that. So it depends. Yeah.
These puffs are created by the stochastic perturbation. How do you know that reproduce themselves or this certain perturbation creates the puffs in the puff stability?
So how do we know that the puffs that are created are the same as the ones?
How do you know the puff is created from the reproduction or from the perturbation?
Well, you can kind of see it in the space-temporal. So, for example, here you can clearly see that there was a puff and there appeared a new puff very close distance downstream.
Here you also have perturbation.
But the perturbation was applied at some time in the very far past over there, and it also has advected itself away from that perturbation, so it cannot have an effect. And we have also what we know is that the puffs they either occur at the point where we do the perturbation, or they occur very close to the puffs which already exist in the pipe. So this tells us that indeed they're reproducing themselves. And yeah. And so the system which at least vaguely should resemble the system of puffs in a turbulent pipe is the directed percolation. So I assume most people here know what direct percolations are, but I'll summarize it briefly anyway. So we have a direct percolation is a model of statistical physics where we have a lattice, and sides of this lattice can be active or passive, and they are connected by edges to the ones in downward direction. And each edge has a probability to be open or closed, and then an active side will propagate down open edges in a preferred direction. So it's why it's called directed percolation. And it's a useful analogy to think of this direction as the temporal direction and this one as the space direction. And if we compare this to the dynamics of puffs, the similarity goes as follows. So if, for example, we start with an active edge and both an active side and both edges are open, then it kind of reproduces itself. It multiplies into two. If both edges are closed, then it decays into nothing. So there is there are no active sites below it at the next stage. And if only one of them is open and the other one is closed, then it just propagates downwards, well, maybe with some shift, some sort of diffusion. And it's very similar to how puffs work. So they can also diffuse themselves, they can also split and multiply, and they can also decay. So at least qualitatively, there seems to be some analogy between these two. And the idea was that maybe this is more than just an analogy, but a more close relationship between these two models. So the direct percolations, the reason why they're interested, they're studied and why they're interesting is that they exhibit a second order phase transition at a critical probability of having an edge open, so the critical density of open edges. And since it's a second order phase transition, we also know all about its critical exponents. So for example, beta measures the density of active sites in equilibrium when we are slightly above the critical probability. Then these critical exponents measure some correlations in space and time. And you can define many different critical exponents. There are only 3 of them are independent, and other ones can be calculated from them. But in principle, all of them can be measured in an experiment with a system like Directed Percolation.
What is the question here? How many paths will be at the end of the experiment? Or?
Yeah, so the question is basically, if we create paths, do they eventually decay into laminar state, or is their splitting sufficient to sustain some sort of density? So this is very closely related to non-equilibrium statistical mechanics, because every path will eventually decay into non-existence, but it may have enough time to create new paths in the process. So there is some equilibrium that is possible, but it may only be possible above a critical Reynolds number. And the key thing about Directed Percolation is that this model is just one of an example of a universality class, which has many different kinds of models. And some of those models which have been studied are even more similar to the dynamics of these paths. Another thing that we know about Directed Percolations is that near the critical point, the correlations in space, correlations in time, and the time to reach any sort of equilibrium diverges. So if we want to probe some physics near critical points of such a system, we need to wait for a very, very long time. And we expect the same to be true for the system of paths in a pipe. And so this analogy was discussed and debated for a while, but it became clear that an experiment or even a direct numerical simulation cannot probe times that are long enough to conclude whether this analogy is indeed there or not. So there was a quest to find a model which would capture all the essential physics of these turbulent paths, but which would allow to simplify the computation as much as possible. And for that, people started measuring the properties of these paths to include in this phenomenological model. And the model that they settled on, I'm about to describe. So in the numerical model, we treat paths as just point particles on a straight line, and they have coordinates which depend on time. And we can induce some periodic boundary condition, for example. And their dynamics is described by the following law, which is obtained from experiments. So the velocity of each path has 2 components. One of them is just diffusion. So as I said, the velocity of paths is not constant. So they will, even if you switch to the reference frame where on average they're stationary, they will still have a diffusion component to them. So we model this as a white noise component to the velocity. And another phenomenon that is measured experimentally is called path pushing. If we have 2 paths close to each other, then the one upstream will interact with the one downstream by trying to push it away from it so that the distance between them increases. So the relative velocity of the paths depends on the distance between them. And this law was measured experimentally, and it turns out that it depends exponentially on the distance to the nearest upstream neighbor.
So this is the phenomenological term, or derived from.
So this was measured experimentally. So this was measured by creating an array of paths equally spaced and seeing how this increases their velocity compared to just a single path. And there was this exponential law which was observed. But then we include this in the model as just the addition to velocity of a point-like particle instead of the full path, which has some turbulent structure, which is very complicated. Next, we need to account for splitting and decaying. But it turns out that the previous view had to be clarified, because the time for a path to decay doesn't only depend on the Reynolds number. Because if we have 2 paths which are very close to each other, and then the one upstream will have that long tail in the downstream direction, which can interfere with the internal structure of the path downstream. And it turns out that that tail will break some sort of structure inside of the path, and it makes it much more likely to decay sooner. So the mean time of decay that depends not only on the Reynolds number, but also on the distance to the nearest upstream neighbor. And this is called path suppression or path killing each other, because a path will try to kill the one ahead of it. And similarly, there is a reverse process of path inhibition, because a path on itself, it wants to split, and it always splits in the downstream direction, because the tail wants to can induce a sufficient perturbation to create a new path. But if there are already two paths at a close distance to each other, then there is not enough room to fit a new one in between them. So the path in upstream will have a much smaller chance to reproduce if there is a neighbor downstream. So we model this by saying that the splitting time depends not only on the Reynolds number, but also on the distance to the nearest upstream neighbor. And both of these functions were measured as functions of Reynolds number and the distance. And so there are fitting expressions for them, and they're all super exponential, because remember that these time scales, they depend very, very sensitively on the Reynolds number, and changing it by 10 or 20 change these decay times by orders of magnitude. But so we can include these phenomenological dependencies into the model. And with these four components, the model is complete. And it can be simulated fairly quickly, because we're no longer limited by simulating the internal structure of these paths. We can just simulate on the time scales where the velocities are relevant, or where the split and decay times are relevant. So this accelerates the modeling process significantly. And the result, I'm going to show on the next slide. So the result was published in this paper in 2024. And so let me talk about this big graph first. This graph measures the equilibrium density of paths in a pipe as a function of the Reynolds number. And the orange points here, they still come from the experiment. And all the blue points come from that model I just described in the previous slide. And you see that in the places where we do have experiments, especially close to this critical point, the experiment measures the model fairly well. But the experiment stops right here. And the model allows us to measure points much, much, much closer to the critical point. And if we plot the difference between the Reynolds number and the critical value of the Reynolds number and the density of paths on a logarithmic plot, then we see that eventually it approaches some sort of straight line. And this solid curve here represents exactly the slope which is predicted by the directed percolation. So the direct percolation predicts a specific value of the slope, which is exactly the critical exponent beta. And we see that the points seem to lie on a straight line which roughly follows the same direction.
But this is double logarithmic
Yes.
plot.
Yes.
And on double logarithmic plot, everything almost goes along lines.
Yes, but this slope is not. This is not a fitting line to the slope. This slope is a prediction of the directed percolation. So the fact that they match is significant. And also, these plots they measure the distribution of gaps between paths. So this one measures gaps between paths at a specific location at different times. So it measures at what times the paths reach this location, and it looks at the tail of this distribution. And this one is the same, but it measures the distribution of gaps between paths in the space direction, and it also measures the distribution. And the solid curves here, the black curves, they're also the predictions of the directed percolation. And we can see that there is a very good agreement between what we find in the model and what the direct percolation predicts. So, and there are also other things that you can measure, which I haven't included in this slide. There are certain dimensionless functions, universal functions, which you can plot, and they also, so the data also collapses to fit exactly those dimensionless functions. And so every measurement confirmed that indeed, close to the critical point, the scalings are all the same as that of the direct percolation universality class. So this paper finally resolved the question of the transition from turbulent to a laminar flow. It gave a prediction, a specific value of the Reynolds number for the transition. It's 2040, and it describes exactly the process by which below this critical Reynolds number, any sort of perturbation will decay into nothing, and above this critical Reynolds number, any perturbation will reach a certain equilibrium density of puffs.
But what units are for density? So
So
5,000 is what?
this is the number of turbulent puffs per diameter length of the pipe.
Diameter.
So diameter is a typical unit of length for the pipes. So yes. For the pipe, you can measure everything in dimensionless quantities. So for example, unit time is diameter divided by the mean flow velocity. And the unit of length is diameter. Yes. So, and this graph also shows, also explains finally why this took so long, why it took so long to get all this data. Because if these points, if we try to obtain these points with an experiment, that experiment in the current setup that is usually used would have to last for roughly 100 years. And the length of the pipe that would be required would be several kilometers, even if not tens of kilometers. And this red point here, it was actually also an experimental point, which was measured slightly below the critical point. And this experiment was running for a month. And even after a month, it wasn't clear whether the equilibrium density is being reached or whether it's in the process of decaying to zero. So this is why it has such a large uncertainty. And after a month, the team had to abort this experiment.
They should go on 1 or 2 years. And error bars will increase.
Well, maybe they should. But yeah, so the length scales required here are on the order of 100 million diameters of the pipe, and the time scales are 10 to the 12. This is a trillion times the typical unit of time in a pipe. So this is completely intractable in any realistic experiment, but thanks to the model which I described last time, it is possible to probe. And even in numerical simulations of the fluid, we cannot get these times. It's completely unrealistic. But thanks to the simplified model, which captured the essential physics of the puffs, we were able to probe these points here and show that they do actually fit the predictions of the direct percolation.
You actually substitute
No. I say we as, sorry, no, I said we as this research community. I actually joined this research group right after this paper was published. So I was, what I was researching is what happens away from the critical point where the direct percolation scaling doesn't actually work. And here, because there is also some interesting behavior, but I haven't included in these slides. Well, I can talk about it briefly after I finish it because I'm actually nearly done. Yes, I'll just summarize the conclusion. So we now finally, after 140 years, we know the value of the critical Reynolds number. It's 2040. And we know that the key role played by the transition from laminar to turbulent flow in pipes is played by turbulent puffs. And we also know that the transition definitely belongs to a direct percolation universality class, and it's actually not the only system in fluid dynamics which belongs to this universality class. It was also shown that turbulence transition in Couette flow also falls in this universality class, and the turbulent transition in liquid crystals is also a member of this universality class. And the character of the transition is such that for Reynolds number below the critical one, if you create any finite perturbation, then after a short amount of time, it will always split into puffs in a pipe. And then after probably a very long time, all the puffs dynamics will split and they will decay, but ultimately they will have to decay to laminar flow with probability 100%. And if you are above the critical Reynolds number, and if you induce a perturbation throughout the entire length of the pipe, and the pipe is long enough, then again, after a short amount of time, any perturbation will decompose into puffs, and the dynamics of these puffs will reach an equilibrium density after a very, very long time. But it will never decay to a laminar state if the pipe is long enough and the perturbation initially occurs throughout the entire pipe. So this finally resolves the question of the transition to turbulence in a pipe flow. And I want to end this talk with a quote from the Reynolds' original paper in 1883, because I think it's remarkable how careful he was with his words and how accurately he predicted the character of the transition. So let me quote. He writes, "It became clear to me that if in a tube of sufficient length, the water were at first admitted in a high state of disturbance, then as the water proceeded along the tube, the disturbance would settle down into a steady condition, which condition would be one of eddies or steady motion, according to whether the velocity was above or below what may be called the real critical value." So he doesn't talk about the linear instability or infinitesimal perturbations or anything like that, which was the main theme in the research of this topic for the next several decades after this paper. But he describes exactly the character of transition, which turns out to be correct, that if a perturbation is finite, it will either decay or it will sustain itself. So yeah, I think it's slightly mysterious that he was so careful and so accurate with his predictions, despite not having any of these experimental data which I presented. But yeah, with that, my slides are also, yeah. Any questions?
So, do you have questions? Okay, let's start.
So, am I right that you're saying that all this scenario with bifurcations as a means to explain the appearance of turbulence is irrelevant?
For pipe flow, yes, it is relevant. For other systems, it's of course known to be relevant. For example, if you have flow past a sphere, then it is of course relevant for many other systems. But for shear flows in Couette flow, in pipe flow, channel flow, it is irrelevant. Yes.
Yeah, but this was considered as some universal scenario of appearance of turbulence. It doesn't matter where in which system. So at least in this sense, it's irrelevant.
Yes, it is irrelevant.
And I have another question. When you substituted your real physical system first experiment, then numerical simulation based on Navier-Stokes equations, this more or less the same physical system. At some moment you substituted it by percolation.
Well, I didn't substitute with
And
percolation.
from percolation you extracted the prediction, which is the native of percolation, this phase transition.
Well,
Or critical flow, but real system, either experiment or simulation with Navier-Stokes equation cannot reach that point. So
Yes.
this means its prediction comes from percolation.
Well, this model is not a percolation model. So, well, at least
Yeah, more or less, you explained it based on the similarity between percolation and these dynamics of these paths.
well, it's not exactly the message I was trying to say. My message was that, well, people expected that the physics will be that of direct percolation, but they couldn't probe it in an experiment. So they tried to simplify simulations as much as possible to get to that regime. And in other systems, for example, in Couette flow, the experiments were, it was possible to conduct experiments that came close to the critical point. So experimentally, we also measured, well, people also measured the correlations.
Okay, can you say that this model indeed describes the solution of Navier-Stokes equation?
Well, phenomenologically, it does describe, and there is a lot of evidence. So in the regimes where experiment is accessible, it matches the prediction, all the correlations and densities very well. So we assume that it would still work even if we came closer to the critical point. Well, some things that can break down, for example. So yes,
it depends how many phenomenological parameters are in this model.
So one thing that can break down is, for example,
you have a lot of parameters. You can model.
Yeah, still a different system. This
Yeah, but they argue that they could use and try to prove it.
One thing that can break down is the assumption of the fact that the paths are memoryless, because when people measure the lifetime of paths, they usually go in time to 1,000, maybe 100,000 time steps to measure these straight lines. But in direct percolation, the timescales are so long that you need timescales which go way higher, and there is a chance that in reality the puffs do age, but very slowly, so that it has never been observed in an experiment, and it's probably not possible to observe it in an experiment. So if that is the case, then maybe this would change the prediction. But if we assume that this straight line keeps going further, then it should be direct percolation.
So, for example, if there is another time scale which appears at much longer times, and this model does not, we don't know this is possible. If there is another time scale, then true behavior will be different from the model.
Yes, well, but we can't know. It's unfalsifiable because it's impossible to measure that in an experiment. So maybe what would happen in a real experiment, for example, in this plot, that maybe we couldn't get experimental points up to here, and maybe we couldn't get to the scaling regime. But if we came even closer to the Reynolds number, maybe like 10 to the -5, then the slope would change. We can't know that because it's impossible to measure that. But the claim is that if the physics keeps going in the way that we measure so far,
it is not the exact resolution of the turbulence problem, because the prediction is derived from another model, not from Navier-Stokes equation.
well,
It's based on assumption that nothing new will happen at longer times.
yes, in a sense, I think you're right. But well, we don't have any reason to suspect that something different would happen. So I think from a physics perspective, this is a completely reasonable assumption.
At least nice.
Yeah.
Okay, do we have?
Still, I don't know why do we call it a second order phase transition.
Well, because it continues.
Just because of this
But why it is continuous? I don't. So because it goes to zero.
Yes.
it has nothing to do with free energy.
Well, yeah, it's a non-equilibrium phase transition, but it is still a second order phase transition.
More question. I have a question about experiments. So, what a typical size of pipes, some diameter, length, which were used in experiments, and so I know several groups. For example, in Manchester, they do some experiment with ultra narrow channels, which are done in van der Waals heterostructures. So, and does this theory can be, or is this theory applied to flow in very narrow channels? Or
well, all of these, like all experiments are based, so people assume that Navier-Stokes equations work. So if you have any modification to the usual Navier-Stokes with no slip boundary conditions, there will be some sort of difference. For example, in nanotubes, there is usually a slip length, which becomes relevant. So it changes the laminar profile. It may change everything here. In the actual experiments, I think the diameter of the pipe is roughly 1 millimeter.
so it is actually large. I mean,
yeah, well, by microscopic standards, it's fairly large. Yeah, the length is maybe the length of this room, maybe a bit longer. And the velocities, I think a couple meters per second. So you can calculate the velocities based on the Reynolds number.
So it's purely classical.
Yes, it is purely classical.
Okay. So if we don't have questions in Zoom, let's finish and send up the picture. Yeah. As a tradition, we present you our sign up for sentence.
Silently.
Спасибо.
Еще раз
Ставь.
Олег оставил, да.
Это спустя? Да.
Подождите, в чате кто-то что-то написал. Что-то не слышно.
They will pause and suppress the nearby of like when it reproduces itself.